up everyone and welcome to today's video. We'll be learning about the tensor product. I'll be working out the processes to solving them, and in another video I will hopefully dive more deeper into understanding it because I only understand the processes themselves as of right now. It actually took me all day to figure that out, which was my goal for today, and we'll work through a couple examples with one of them being an exercise from the Quantum Computation book by Nielsen and Chang. The tensor product of x and y can be seen as the possibilities of vectors that can exist inside this product space, and we can view it as 0 times y, 1 times y, 1 times y, 0 times y, giving us 4 possible vectors to be represented. In vector 1, we see that it's the tensor product of our 0 basis on the x gate with 0i. So how can we figure that out? It really shows us that it's 0 times 0, 0 times I, 1 times 0, and 1 times I. Computing that would give us 0, 0, 0, I as a column vector or a ket. For vector 2, we see that it's the tensor product of 0, 1, negative I, 0. And we can solve this by actually doing 0 times negative I, 0 times 0, 1 times negative I, and 1 times 0, giving us the result 0, 0, negative I, 0. And for our third vector, we see that it's the tensor product of 1, 0, 0, I, which would give us 1 times 0, 1 times I, 0 times 0, and 0 times I, and computing that gives us 0, I, 0, 0. For our fourth vector, it is a tensor product of 1, 0 with negative I, 0. And this gives us the computation 1 times negative I, 1 times 0, 0 times negative I, and 0 times 0. Computing that would give you negative I, 0, 0, 0. Let's put it all together. What does this all mean, and why do we have 4 different vectors? Well, putting the 4 vectors together actually gives us the tensor product of x on y, which is 0, 0, 0, I for our first column, 0, 0, negative I, 0 for our second column, and 0, I, 0, 0 for our third column. And for our fourth column, it becomes negative I, 0, 0, 0. And this is actually the result of putting our vectors together, which is the 4 possible combinations that can exist inside this tensor product. And if you take a closer look, you can actually see that the zeros are diagonalized and the i's are diagonalized, even though they alternate between I and negative I. What's the tensor product of y on x? We can see that it's the same thing except reversed. So we do 0 times 0, 0 times 1, I times 0, and I times 1, giving us 0, 0, 0, I. For our second step, we need to find the second vector, which is the tensor product of 0i and 1, 0. Doing this multiplication gives us 0 times 1, 0 times 0, I times 1, and I times 0, and the result would be the column vector 0, 0, I, 0. Doing this to the third vector will give us negative I times 0, negative I times 1, 0 times 0, 0 times 1, which results in the vector or the column vector 0, negative I, 0, 0. And lastly, for our fourth vector, we find the tensor product of negative I, 0 onto 1, 0, which gives us the result negative I times 1, negative I times 0, 0 times 1, 0 times 0, which results in the column vector negative I, 0, 0, 0. Putting all these together, you see that it results in the first column vector being 0, 0, 0, I, the second column vector being 0, 0, I, 0, the third column vector being 0, negative I, 0, 0, and the fourth column vector being negative I, 0, 0, 0. This differs from our tensor product of the x gate onto the y gate. It has to do with symmetry, which is the last part of the exercise that I was working through in the Quantum Computation book, and that's actually one of my goals for tomorrow, is to release a video understanding what symmetry has to do with tensor products. So now let's figure out the tensor product of the x gate onto the z gate. It can be seen as 0 times 1, 0 times 0, 1 times 1, and 1 times 0 for our first column vector. Our second column vector is seen as 0 times 0, 0 times negative 1, 1 times 0, and 1 times negative 1. Our third column vector is then 1 times 1, 1 times 0, 0 times 1, and 0 times 0. With our fourth column vector and our last column vector being 1 times 0, 1 times negative 1, 0 times 0, and 0 times negative 1. We get our tensor product of the x gate onto the z gate to be 0, 0, 1, 0, 0, 0, 0, negative 1. Sorry, there's a lot of zeros. 1, 0, 0, 0, 0, negative 1, 0, 0. Last part of this exercise. So we'll first start with the tensor product of the x gate onto the identity matrix. And we see that the first column vector becomes 0 times 1, 0 times 0, 1 times 1, and 1 times 0. The second column vector becomes 0 times 0, 0 times 1, 1 times 0, and 1 times 1. Our third column vector then becomes 1 1 times 1, 1 times 0, 0 times 1, and 0 times 0. Now our last column vector is 1 times 0, 1 times 1, 0 times 0, and 0 times 1. We get the tensor product of the x gate onto the identity matrix to be 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0. To do our tensor product of the identity matrix onto the x matrix, we see that the computations needed to do this are the first column vector, 1 times 0, 1 times 1, 0 times 0, and 0 times 1. Our second column vector becomes 1 times 1, 1 times 0, 0 times 1, and 0 times 0. Our third column vector then becomes 0 times 0, 0 times 1, 1 times 0, and 1 times 1. With our last column vector becoming 0 times 1, 0 times 0, 1 times 1, and 1 times 0. This results in the matrix 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. I hope you enjoyed today's video. I wanted to keep it as short as possible while sticking to the same process. And if you didn't fully understand it, check out the GitHub link. Thank you for tuning in. Keep learning.